Liquid crystal emulsions bridge the gap between order and fluidity, combining the precision of crystalline structure with versatility of emulsion to revolutionize drug delivery. Greetings everyone. Today I'll be presenting my work on advanced topical formulation of terbinafine using liquid crystal emulsion technology, which focuses on enhancing skin permeation and achieving sustained drug release using a novel dosage form. Fungal infections are common, especially in warm, moist areas of the body. Apart from the physical discomfort, they often lead to social stigma. Conventional topical antifungals suffer from poor skin penetration and frequent reapplication requirements. Hence, there is a clear need for a better formulation. Terbinafine, an allyl amine antifungal drug. It is classified as BCS class 2 drug with low solubility but high permeability. It is fungicidal and shows high affinity to keratinized tissue, making it ideal for deep skin infection. However, its limited solubility limits its efficacy. Our goal was to develop a liquid crystal emulsion formulation that mimics skin lipids, improved solubility, enhances skin permeation, and enables sustained drug. The main aim of the study was to formulate a liquid crystal emulsion of terbinafine to enhance its skin permeation and controlling its release by delivering the drug deeper into the skin layers. The objectives were screening the oils and surfactants via solubility for liquid crystal emulsion, construction of pseudo-ternary phase diagram, formulate, optimize and evaluate the drug-loaded liquid crystal emulsion, develop and assess LCE-loaded gel system. Various oils and surfactants were screened for preparation of the emulsion. Lavender oil was selected as the oil phase and tween 80 as a surfactant due to its good solubilizing potential. We created pseudo-ternary plots using various ratios of lavender oil and surfactant to find the optimal emulsion region. The best ratio was found at 1:7 ratio of tween 80 is to lavender oil. Further, this 1:7 ratio was explored for studying the different phase diagrams, which indicates the multiple phasic regions of the emulsion. To prepare LCE, we took two solutions, aqueous phase and oil phase. Aqueous phase containing water and tween 80, oil phase having the drug and lavender oil, which was heated to 70 degree centigrade. After that, the oil phase was added to the water phase by stirring continuously at 3000 rpm for 15 minutes, which gave us our transparent liquid crystal emulsion. We used a 3:2 phase-centered central composite design to optimize critical formulation parameters. Key attributes evaluated were the droplet size, the refractive index, the PDI. Various 3D surface plots help to visualize variable effects, and the polynomial equation help us to understand the relationship between the independent variables and the dependent variables. We found that droplet size had a linear relationship with the independent variables, whereas the refractive index had a quadratic relationship and PDI had a linear relationship with the independent variables. Further, the model validation was done using checkpoint formulation, where the predicted value were almost similar with the actual value and there was no significant difference between them, enabling us to understand that the model was validated and it is significant. Next, the optimized formulation was confirmed for its crystallinity formation. So for this, polarized lens was used. Light was passed through the polarized lens and these colorful regions, bright regions, proved that there was presence of crystalline structures in the optimized formulation. Further, the drug release of the liquid crystal emulsion was performed both in vitro and ex vivo, where we saw a slower drug release till 25 hours, where only 50 to 45% of the drug was released. Next, the morphological structure of the optimized LCE was performed, where the physical appearance of LCE is depicted in this picture. Next, we also checked the appearance of LCE under optical microscope. which was similar to what we see for any oil and water emulsion when it is focused under an optical microscope. Next, this LCE was focused under polarized microscope where we got structures like this, where these black droplets proved the presence of crystalline structures. Further, the PDI was also measured, and we found that the particle size was in the range of 14.24 nanometer and PDI was found to be 0.45. Now, the prepared liquid crystal emulsion was to be loaded into gel. So for that, various polymers were screened, among them carbopol 934, HPMC E15, and combination of chitosan and alginate was used, where we found HPMC E15 showed us better results based on the various physiological parameters. Further, the HPMC E15 various concentration were screened, and in that 2.5% of HPMC E15 showed us the best result, and it was further used for loading our LCE. So this picture depicts the gels formed from different concentration of HPMC, and here it shows the gel formed by 2.5% of HPMC. The physiological properties found were the pH was around 6.3, viscosity 3799 CPS, and spreadability was 5.8 centimeter per second. Next, the crystallinity was confirmed whether it was retained after loading into the gel. So for this, polarized light microscopy was used, where we focused our liquid crystal emulsion under the light microscope, and we got this kind of result where these bright structures showed us presence of crystalline structure. Next, we also focused our gel, where we found that it represents the presence of a semi-crystalline or anisotropic domain in the LCE loader. Further, the retention of crystallinity in the gel was confirmed by small angle X-ray scattering, where we found that high intensity at lower Q values indicated the presence of large crystalline arrangements within the gel, proving that our formulation had crystalline particles in it. Further, a last confirmation study was done using negatively strained cryo-temp, where we found these kind of spherical structures. We found these spherical structures because the highly ordered crystalline structure self-assembled itself into this spherical structure in the presence of high surfactant concentration, giving a micellar kind of a structure, hence proving that our formulation had crystalline entity. The skin retention study of an optimized gel loaded with LCE was found to be 6.105 mg per centimeter square, which ensured that the drug was showing localized action. Further, comparative drug release was performed for the pure drug LCE and LCE loaded gel, where LCE loaded gel showed 70 to 80% of the drug release by 25 hours. Further, drug release kinetics was done for LCE and gel, and the results were found to be following Cosmias-Pepper's model, and the N value was between 0.5 to 1, ensuring that it followed diffusion and relaxation of the polymer responsible for the drug release. Antifungal activity for the optimized LCE and LCE loaded gel was performed, and it was found that 1% LCE loaded gel had superior readings and results compared to the Triaza 1% concentration cream which is present in the market. The LCE and the gel showed good physical and chemical stability over time, confirming suitability for long term. To conclude, we successfully formulated terbinafine loaded liquid crystal emulsion gel that improved drug solubility, skin permeation, retention, and antifungal efficacy while ensuring sustained release. The future prospectus is, in the future, this formulation approach can be extended to other poorly soluble topical drugs. In vivo studies can further validate therapeutic potential, and this system can be scaled up for industrial production. Thank you, one and all, for listening to me.